Okay, so my student is in Saudi Arabia, so I'll be presenting the work. This is with also an undergraduate, Dan Lemmond, who directed. So I'm going to be talking about chainlets, which is a new kind of description for detection and recognition, and I'm going to buck the trend. This is not deep. Nothing in this is actually, there's some deep stuff because we're going to compare against deep and beat them. So traditional feature descriptions can be used in lots of vision problems where there simply isn't enough data to do deep network training, or they can also be computationally efficient. So we wanted to do some stuff. There was lots of good work in using HOG, Histograms of Oriented Gradient. HOG's a pretty good feature descriptor, but it still has some problems because the way it's combining data, it doesn't actually understand objects in a sense. There's no connectivity across objects. They're just little patches of HOG features. So my student and I started looking at what can we do. To be honest, it was Adil's idea, right, to think, I'm going to do something better. So how many people here know what a chain code is? Right? Anyone? Oh, we got a couple. Good. Right. Chain codes are old. In fact, they were invented in '61, so they're probably older than anyone in this room. Right? But maybe not. So a chain code is a representation of how do we deal with boundaries or edges in an image, and you pick a pixel, you start from them, and then you basically make a code that says if I go this way, it's a 0, this is a 1, this is a 2, and you represent everything by walking around. And there's actually two kinds: an absolute chain code and a relative chain code. In absolute chain codes, this is always 0, this is always 1 as I move around the image. In a relative chain code, think of it as walking along it, and as I turn, I change my code. So I can take an image, I compute a bunch of images, edges from that image, and we make our chainlets by now taking those edges extracted, put little boxes, put our chain codes in them, where we now compute 0s and 1s depending on which way I walk. So on this edge, I go 0, 0, 7, 7, 6, 7 as I walk along the edge, and I get a bunch of stuff, and that allows me to build an absolute chain code histograms, because I got 2 zeros, a couple of 6s, and a couple of 7s, and that's my representation of that patch. Then I do overlapping blocks of different things, and I put them together. Now, why is this interesting? Well, absolute chain codes are actually useful, so if I do this red line here, I get 6, 7, 5. Right? This is representing a particular curve. And now I'm effectively matching curve shapes from one image to another. So here's a reflection of the ear, and the absolutes match in an absolute orientation sense. The blue ones, which are relative, actually match exactly, even though I did a flip of the image. They're rotation and position independent, where the absolutes are position independent but not rotation. For some targets, like pedestrians, we don't actually want to detect things sideways. We want upright pedestrians in general. So when we go to do pedestrian detection, we'll find out that absolute work better. And when we're doing ears, where heads can rotate, we'll do relative. And so we can then build these histograms out of overlapping patches. Now here I've done the whole ear, but in reality, we do like a 64 or 32 by 32 or 64 by 64 patch and move it over the image to build our histograms. Idea is otherwise very much like HOG. We just changed, instead of histograms of oriented gradients, we're doing histograms of chain codes. And that gives us our representation. So how well does this idea work? It seems pretty simple. So here we have the INRIA pedestrian detection results. Here's a whole bunch of different algorithms. HOG's way up here. There's a bunch of algorithms. One of these is based on deep features. And we did better for most of this curve than everything except for a little bit of the spatial pooling. There actually is a new deep feature algorithm that came out actually about a year and a half ago, where the deep features were combined with random forests, and they're better than that. So we're only the second best algorithm out there. We studied, if you step by the poster, we can talk about the ablation study. We looked at what matters, relative versus absolute. Should we do a sliding window, deformable parts models, or edge boxes? Should we look at other kinds of things, like how do we measure errors? So a full ablation study, I can talk about those in detail when we get there. The second problem we looked at was unconstrained ear recognition. An odd biometric, recognizing people from their ear. There's a data set that came out, and there was a challenge. We did some simple pre-processing, and then we took part in the challenge. We don't get the test data. We only get images. We give them the results. They score them. And we did significantly better. We're the red line. These are the other participants in the challenge. They actually looked at a bunch of standard features and a bunch of deep feature algorithms. And we were significantly better than all of those things, right? So deep features are not the best for ear challenges, and we had an ablation study about that, so stop by our poster and we can chat about all those details. Thank you.